Hi guys, Dr. Kruse here. I'm going to work some simple and probabilities, the probability of the first event and the second event happening. So for example, if you have a shuffled deck of 52 cards and you're going to draw 2 cards in a row, successively means in a row, all right? So if you deal those 2 cards, it depends on whether you put the first card back or not on the probability of the second event. The probability of the second event might not change, or if you keep the card and you don't put it back, the probability of the second event might change. So let's calculate the probability of drawing a black card and then another black card with replacement. That means I'm going to draw the black card the first time and I'm going to replace it. I'm going to put it back in the deck and then calculate the second probability. So we can abbreviate this if we like. The probability that the first card is black and the second card is black. All right. The probability rule states that if you're doing an AND situation, it's the probability of the first event times the probability of the second event. But keep in mind that the first event has happened. You have to keep in mind that, yes, they did draw a black card on the first event. And you also have to keep in mind that they put the card back. You have to keep all that stuff in mind. Technically, this says given that the first event happened. All right, so one more time. Probability of the first event, that's usually pretty easy to calculate, times the probability of the second event, given that the first event did indeed happen. So you can't calculate the second event until you take into account what happened on the first event. All right, did it happen? Yes. Did they put it back? Yes. Okay, now we're ready to calculate probabilities. So the probability of drawing a black card, well, there's 26 black cards. There's 13 spades and 13 clubs. There's 26 cards, 26 black cards out of a total deck of 52 cards. All right, so assuming that we did draw a black card on the first draw and that we did put it back, now what's the probability that we draw a black card on the second draw? There's still 26 black cards in there out of 52. So the probabilities don't change, all right? Given that we drew a card and we put it back, the probabilities will stay the same. Multiply these out. You can talk fraction, you can talk percent. In stats, we usually answer as a decimal. So there's about a 25% chance that you can draw a black card, put it back, and then draw another black card. All right, let's work the exact same problem. What's the probability of drawing a black card, not putting it back, and then drawing another black card? So the probability you draw a black card the first time and the probability you draw a black card the second time. Well, an AND probability is the multiplication rule. So it's the probability of the first event times the probability of the second event, given that the first event did happen, all right? So the probability I draw a black card on the first draw, that's still 26 out of 52. Now this time I'm not going to put it back, all right? That changes things. So given that I drew a black card and didn't put it back, what's the probability of drawing a black card now? Well, now there's only 25 black cards. And there's only 51 cards in the deck. I didn't put that card back. So I have one less black card and I have one less card in the deck. So the probabilities change when you don't replace the card, all right? When you say without replacement, probabilities will change. Multiply, and our percentage is a little bit lower. The first one with replacement was 25%. This is a little bit lower than 25% if we don't put the card back. All right, what about dealing 2 cards in a row, and you put the first one back with replacement, and you want to find the probability the first one's a king and the second card's a queen. So the probability of drawing a king and then drawing a queen. Probability of drawing a king times the probability of drawing a queen, given that you did draw a king the first time and you put it back. All right, so the given that part is important. All right, you got to think about, yes, they did draw the first event, they did draw the king, and they put it back. Okay. What's the probability of drawing a king? Well, there's 4 kings: king of hearts, king of diamonds, king of clubs, king of spades. There's 4 kings out of a deck of 52 cards, times, all right, what's the probability of pulling a queen? assuming that you did pull a king, all right? So think about it. There's not a king in the deck. Oh, wait, I'm sorry. With replacement, I messed up. We pulled a king and we did put it back. My bad. So now what's the probability of pulling a queen, given that you did pull a king and put it back? Well, how many queens are in the deck? 4 queens, just like the kings, out of a deck of 52 cards. The probabilities did not change because we put the card back. Multiply it out. There's less than a 1% chance of that happening. This is 0.59%. That's less than 1% chance. Okay, so now let's calculate the same thing without replacement. So we're going to draw the king on the first draw, but we're not going to put him back. And then we're going to calculate the probability of drawing a queen on the second draw. So first card's a king, second card's a queen, and you didn't put the king back. You didn't put the first one back. So the probability of a king on the first draw and a queen on the second draw without replacement is the probability of a king times the probability of a queen, given that you did draw a king the first time and not put him back. Probability of drawing a king, there's 4 kings out of a deck of 52 cards, times, now what's the probability of a queen, given that you drew a king and did not put him back? Well, there's still 4 queens, all right? You drew a king, you didn't draw a queen. So you drew a king out, there's still 4 queens, but there is 1 fewer cards in the deck, because that king that you drew out, you didn't put him back. All right, so you got to pay attention, because sometimes both numbers change, sometimes just one number changes. But without replacement, you can count on the probabilities being different. And again, we have a less than 1% chance of that happening. Okay, let's take another look at this. But instead of using a deck of cards, let's use kind of a different word problem. So a batch consists of 12 defective coils and 88 good coils. That's a total of 100 coils. Just imagine these coils are in a box or whatever. And in this box, this batch of coils, 88 of them are good and 12 of them are bad. Find the probability of selecting 2 good coils. All right, so you're going to reach in, grab a coil, and then you're going to reach in and grab another coil. When 2 coils are randomly selected, if the first selection is not replaced, so that's without replacement, before the second one is made. So you're going to reach in this box that has 100 coils in it. You're going to pull one out. You're not going to put it back, and then you're going to reach in there and pull a second one out. Now remember, you did not put the first one back. All right, and we want the probability of selecting 2 good coils. So it's the probability that the first coil is good, and then I reach in and I grab another coil and the second coil is good. So the probability of reaching in there twice, and the first one's good and the second one's good. All right, an AND problem, that's the multiplication rule. The probability that the first coil that I grabbed was good times, now I got to do the probability that my second coil will be good. Now remember, the first one was good, all right? And I did not put it back. All right, I did not put it back. Oh my gosh, I made a mistake. I got to fix this problem here. I just now saw it. I'm going to correct this real quick. Whoops. Well, I'm glad I caught that. Okay, let me start over. I had to make a correction here because I messed up. There weren't 99 coils left. So let me start over. All right, let's first of all start with the probability of just reaching in there one time and selecting a good coil. Well, there's 88 out of the 100 coils are good. So I can use 88 out of 100, or I can use 0.88, either one. What's the probability of reaching in and grabbing a good coil, not putting it back, and then grabbing a second good coil? Well, that's the probability of grabbing a good coil, 88 out of 100. There's 88 good coils out of 100 in the box, times, okay, now what's the probability of reaching in there a second time and grabbing a good coil, assuming that I got a good coil on the first draw and did not replace it? All right, so think about that. Well, now, since I didn't put it back, now there's only 99 coils in the box. And how many of them are good? 87 are good. All right, remember we pulled a good coil the first time. So there was an 88 out of 100 chance of pulling a good coil. Now, given that this happened, given that I pulled a good coil on the first draw Now what's the odds or the probability of pulling a second good coil? Well, now there's only 87 good coils in the box out of 99 total coils, for about a 77% chance of that happening. All right, I'm going to do one more problem with you here. Now, in one town, it says 76% of the adults have health insurance. What's the probability 8 adults, selected at random from the town, all have health insurance? Now notice this is a different kind of problem. They didn't tell us how many total adults we have in the town. It's not like the deck of cards where we had 52 cards total. And it's not like the coil problem where we had 100 coils in the box. All right. All they're telling us is that in this town, I mean, there could be 1,000 people there. There could be 10,000. We don't know how many adults, but we know that 76% of them have health insurance. So when I'm talking about randomly selecting an adult from the town, just imagine that maybe you're in a classroom and the town is outside the classroom. And maybe you just open up the door and you randomly grab an adult from the town. All right. There's just all these thousands of adults outside the door, and you reach out there and you grab one. What's the chance that that person has health insurance? There's a 76% chance that that person has health insurance. Now, whether you put that person back out in the hall or not doesn't really matter. I can open the door, I can reach out and grab another person from the town, and the chance that that person has health insurance is also 76%. Nothing about the first adult is going to change anything about the second adult. All right, think about that. If there's a 76% chance that any adult in the town has health insurance, then if I pick the first adult and he does have health insurance, that's not going to affect the odds of the second adult or the third adult or the fourth adult that I pick. They're each going to have a 76% chance of having health insurance. No matter how many times I reach out in the hall and grab an adult, there's going to be a 76% chance that they have health insurance. So what's the probability that I can reach out into the hall 8 times and every one of those 8 adults that I grab at random has health insurance? So what I'm saying is the probability of the first person I grab that I randomly select has health insurance, and the second person and the third person and all the way to the 8th person. All right, this is kind of like a Vegas bet. What are the odds that I can grab 8 people in a row and never miss that each one of them has health insurance? All right, sounds like a craps game or something where you're rolling the dice, and you just keep winning. So since this is an AND rule, we're using the multiplication rule. Now I'm cheating a little bit. I'm supposed to say the probability of H2 given that H1 happened. Well, I'm cheating a little bit. Since the probability is not going to change, I don't really need that given that part on the equation, on the formula. So it's just going to be the probability the first one has health insurance, 76%, or 0.76 is easier, times the second one, it's still 76, times the third one, fourth one, fifth one, sixth one, seventh one, and then times the 8th one. When you leave out a bunch here in the middle, you can get away with doing a ... That says all the people in the middle of the series were left out, but they're there. All right. So I'm saying 76% for the first one times 76% for the second one times all of those times 76% times another one. All right. So I have 8 of these. 1, 2, 3, 4, 5, 6, 7, 8 of these 76% all being multiplied together. So you can punch all 8 of those in and hit times, or a quicker way is 0.76 raised to the 8th power will get you to about 11% chance that I can reach out into the hallway 8 times and get 8 people with health insurance. There's only an 11% chance that that'll happen.